Is Ashutosh mic okay? Perfect. Okay. So we are doing this as a discussion, but I think I'm just going to put out some points and then I'm going to maybe get you to comment and then maybe invite a few questions. Yeah. Again, the request is please one question only once you get the mic. If we still have time, we'll come back to you. So we want to give everybody a chance. Just please keep that in mind. So we've been talking about, QoS, we've been talked about security, some Wi-Fi 7 performance. Of course, Ashutosh has worked on standards, products, etc., with a lot of emphasis on physical layer evolution. So we just thought maybe we'll pose a few questions to him, in terms of whether it has been hit, miss, or maybe combination of both. So we've discussed that. So what we did was maybe pick up a few points and just to kickstart discussion, and then let people come in terms of questions. So maybe Ashutosh, I'd like you to maybe...
Yeah, okay. So just before I get started, how many of you know about the physical layer of Wi-Fi, layer 1? Just a brief, it's about 10-15% of the audience. Okay, thanks. So yeah, maybe I can just go through it, right? So the first question is that, we talk about physical layer, which is the main pipe, the lowest in the Wi-Fi stack. So we have already seen there are Wi-Fi standards right from Wi-Fi 1 to Wi-Fi 8, spanning more than 3 decades. So here, like, if there is a choice, somebody gives you a menu, OFDM, MIMO, bandwidth expansion, MCS enhancements, right? Now, I worked in this domain for more than, I would say 10, 12 years. What typically happens is, let me go one by one. It'll be a little bit pedagogic, so just bear with me. If you go to OFDM, if you see any kind of wireless technology, whether it is wireless LAN, whether it is cellular, 4G, 5G, 6G, you normally have OFDM as the physical layer modulation technique. It's been there in Wi-Fi for more than 25 years. The reason is that it is very well suited for Wi-Fi, considering the fact that we can use an FFT at the receiver, we can use an IFFT at a transmitter, and nothing has come close to it, for delay spread and multipath channels. So pretty much even going forward for the next generations of Wi-Fi, we'll have OFDM coming up, and I don't think that's going to be replaced by anything. People tried NOMA, people tried OTFS. OTFS might have some potential, let's see how it pans out, but otherwise pretty much I would say OFDM is here to stay. So in the next one, which is MIMO, which is what Dr. Srikanth has put out, as you all know, right, when you have multiple antennas at the transmitter and at the receiver, you can keep going from 2 antennas to 4 to 8, people can even go higher than 8. That's one good thing, that you can keep sending multiple parallel information streams when you have MIMO, multiple input, multiple output. The problem is not at the transmitter, it's also at the receiver, because when you receive all the mixed streams at the receiver, you have to separate them, then do demodulation, decoding, and a lot of processing which happens. Those who are aware of physical will know that. It's easy for 2 streams, very easy for 2 streams. It gets a bit harder for 3 and 4 streams. But if you go beyond 4 streams, usually there is this thing called MIMO equalizer. You have maximum likelihood, MMSE, zero forcing and all that. That design in hardware with a low area becomes very challenging. So typically you will see that many of your access points or hotspots, even in enterprise, they will typically go up to 4 streams. And then they'll start using a mesh of access points. This is called, mesh, Wi-Fi mesh, self-organizing network and all that. The other thing, which is my favorite topic, is this bandwidth expansion. So those of you who have been following the Wi-Fi standards, you know that initially we only had 20 megahertz in 11A, 11G, which was in 1999. We fast forward to 2025, right? We have 320 megahertz in the latest Wi-Fi 8, even in Wi-Fi 7. Now, what happens with the bandwidth is, if wishes were horses, you definitely have 640 megahertz, 1280 megahertz and all that. However, you want to operate in the unlicensed band. You need your telecom authority, FCC or ECC, or in India we have DOT and TRAI, to give you that much bandwidth in the unlicensed band. That's where it gets challenging. So you have 2.4 gigahertz, 5 gigahertz, 6 gigahertz and all that. I think recently the government said they're inviting bids to open up the 6C band, lower band, right? That's going to be another 500 megahertz. The point is that if you want to now double from 320 to 640 megahertz, who's going to give it to you? Right? There are already incumbent players. There is cellular who have a licensed bands. There's military. There is civil engineering, EMS, emergency service and all that, right? So for that reason, you cannot keep saying that I want higher and higher bandwidth. It has to stop somewhere. Now, if you want to directly jump from 320 to higher bandwidths, you want to go into the gigahertz regime, right? Then you have to go to millimeter wave, 45 gigahertz band, 60 gigahertz bands and all that. That's also one way in which we can look forward. MCS. Now, the thing with MCS is that it's a modulation and coding scheme combined. Here, you can typically go up to 1K QAM, 1024 QAM or 4096 QAM. The problem is not about trying to make it more and more dense. The problem is that if you want to make the oscillation diagram much and more dense, you have to have that much EVM. Like at the transmitter, you have this thing called error vector magnitude. So you have to have an EVM of minus 38 dB for 4096 QAM. If you want to go to higher QAM, you have to have 3 dB better. Now that's very, very challenging from a hardware design point of view. The RF chip, for example, right? Not very easy to get minus 41 dB or even more strict than that. OFDMA is a little interesting in the sense that you want to have fractional bandwidth. Like you can have RUs, those of you know Wi-Fi 6, Wi-Fi 7. You can have RUs, you can have people getting kilobits per second rate, like for example voice. On the other hand, people watching HDTV or doing interactive game, you can have megabits or you can have tens or hundreds of megabits per second. OFDMA has helped in that sense. You can have heterogeneous QoS requirements and you can have many, many more users than you can normally support with Wi-Fi. Now, MU-MIMO is very, very interesting topic. Those of you who are aware of physical layer, I'll just tell you about MU-MIMO in brief. So what MU-MIMO does in downlink is as follows. You have a single access point. It could be in your home or enterprise. You have multiple clients. In the same time interval, simultaneously, you want to send traffic to all of them. Okay. So you do something called downlink channel sounding. The different stations give the feedback, channel feedback. And then the access point does some mathematical operations called precoding and sends to all of them in one shot. The thing with MU-MIMO is that you can go up to a certain number of special streams or a certain number of clients. Beyond that, it becomes very difficult to make that precoding matrix. It's a mathematically challenging topic. Of course, there's a lot of research in this topic also. Now, what happens with MU-MIMO is that it's not only about how you do precoding. You can always use machine learning, AI to make it better and better. But at the receiver side, once again, are you really going to get that much benefits? If you want to have 6 clients, 7 clients, etc., it's very, very challenging. But nevertheless, all these topics, I would say, whichever Dr. Srikanth mentioned, MIMO, MCS, MU-MIMO, they definitely are something which can be tackled in the upcoming Wi-Fi standards, especially at the physical layer. I can have more follow-on questions.
Thanks. So can we involve the audience also, Ashu? Is it okay?
Sure.
Yeah, so maybe if you have questions specific to this, put up your hand. Maybe while the mic gets to you, maybe I'll just ask you to comment.
Yeah.
Which would you take as probably the most important in terms of having made an impact in the physical layer evolution, if you had to take a pick?
If I were to take a pick, it's MIMO.
Okay. So MIMO. So Nadeem? Yeah.
So the question is about OFDMA.
Yeah.
What will it take to make OFDMA as successful as it is in LTE and 5G?
Yeah, that's a good question. See, the thing is, in Wi-Fi, it started with resource unit, RU. We have different RU sizes in Wi-Fi 6. Wi-Fi 7 went to multi-RU. You can have 2 discontinuous RUs, you can put them in one entity. Then Wi-Fi 8 has gone to DRU, discontiguous RU, DRU, right? Now, it remains to be seen as to how much more generalized you want to make it. Okay, I think with Wi-Fi it's not about really trying to densify things, because see, people try to go the densify way, which happened from Wi-Fi 6. It's not really succeeded very well. But I think where Wi-Fi should focus on, which is what's happening with Wi-Fi 8, is that you have done very well on the bit pipe, the GBPS that you're giving. You've already done much better than LTE also, right, or 5G. However, you start looking at latency, because you don't look at latency, then gamers won't be happy. People doing interactive video calls will not be happy. So I believe OFDMA in Wi-Fi has got limited success, to be very frank. Okay. Better thing is that start looking at latency, start doing some cross FiMac design. That will be a better way to go.
We can take, please put up your hands if you have questions so that Mike can come to you. So, Ashok, yeah. Keep your hands up so I'll know I can direct the mic runners to you. Yeah, quick.
Ashutosh, Ashok here. If you could comment about aspects related to the power amplifier, right?
Yeah.
Considering that we are going ahead with the size of the constellation, right? 4096 QAM and whatnot, and
correct.
The fact that OFDM is here to stay with PAPR and related stuff.
Okay.
If you could maybe comment on the power amplifier aspects of Wi-Fi TX.
Okay.
Yeah.
I have limited knowledge, but I'll just do my best here. See, what happens with, just for the audience in general, right? The power amplifier is something which takes your RF chip output. Okay, it will be at a very low power, but you want to send an electromagnetic wave over the air. So it can give anything between 20 and 30 dB of attenuation, because you want to send that thing over the air with 50 ohm impedance and all that. Now, what happens with the power amplifier is that it is never linear. Okay, so it will have some kind of an S-shaped curve, where as you go to higher and higher input power versus output power, the distortion increases. So you really want to send more dense constellations like 1K, 4K QAM, but unfortunately for that you need more linearity, which means you have to back off higher and come to the linear part. Okay, that's why you will see that with any kind of a practical transmitter, whether it is Wi-Fi or even if it is in cellular, right? You get the highest range only with the lowest MCS, because only with the lowest MCS, that is BPSK, QPSK, you can operate at the highest point, and then you can get the highest power out over the air. Now coming to what the person mentioned, right? See, what happens with power amplifier is that I'm pretty much aware that there are lots of designs where you want to linearize it as much as possible. Okay, you are getting to better and better technologies. We are even trying to see whether we can leverage something where we can have, a combined power amplifier and some of the front-end components of the RFIC, in a single monolithic unit. There are some researches happening in low-power wireless, IoT, and all that on that front. But otherwise, what happens is that the power amplifier, I think there are various classes. I don't know much about that, A, B, C, D, and all that. There is going to be a lot of work happening on the PA front because when Wi-Fi now tries to extend its range, because see, Wi-Fi pretty much has been indoors. All of you have Wi-Fi here in the hotel also, right? But now there are people are talking about using Wi-Fi for next step outdoors, drone control, just out on the street and all that. There, if you want higher range, you want to overcome all the obstacles and the attenuation, you need to have better power amplifiers. So the research on that is definitely very, very important, I would say. I'll give you one historical thing, right? 2009, WiMAX was there. It died out very fast, okay? And I know people who worked on this topic from my previous careers and all that. WiMAX died because it did not have a good PA design. Many of the companies working in WiMAX. And that's where LTE came. And because they were able to operate with a much better PA design for their modulation technique, it was able to succeed. So even power amplifier can pretty much kill or make a technology, a small component.
Okay.
Thank you.
So,
yeah.
Maybe we'll move on to the next topic, maybe get your comment and then involve people.
Yeah, sure. Good questions. So here the question is that high-end clients have not typically gone more than 2 streams. I'll give a mixed bag answer here. See, when we say clients, right, most of us use the client in the form of our mobile phones. You have Wi-Fi and use that in your homes and enterprises, right? Typically what happens is that we look at 3 metrics. We look at power, performance area, PPA. Those who work in the Wi-Fi world will know that part. Now, if you look at a form factor of a mobile, it's difficult to keep more than 2 antennas, 2 transceiver chains. Okay. So for that reason, if you have got 2 chains, you cannot go more than 2 spatial streams. You go to slightly bigger form factor, you go to say tablet. There some people are trying to do 3 or 4 chains and you can have 3 or 4 streams consequently. See, the second thing is that how much data do you want in a given mobile phone? Even if you want to use it as a hotspot, you really do not need much. Rather, you would focus more on how to have more advanced schemes like carrier aggregation. In the case of Wi-Fi, maybe you can have 2 streams, 2 antennas, and you can have Wi-Fi 8, which can take you to 320 megahertz and much more better, rates and latencies and all that. So typically what happens is that getting beyond 2 streams is not practical for a client. You would rather have all the heavy-duty stuff happening at the access point, which can go 4 or even higher number of on 4 streams. Higher bandwidth, favorite topic. Okay. See, the beauty about OFDM, okay, I think I'm outselling OFDM here, is that the only reason you can keep something so successful is that even if you go higher and higher bandwidth, the channel equalization is very, very easy in OFDM. It becomes single tap channel equalization. Those of you who know the theory behind it will be able to appreciate this. So even if you go from the lowest 20 megahertz, which was there in Wi-Fi 3, 11A or 11G, and fast forward 25 years to today, we have Wi-Fi 7 and 8 with 320 megahertz. The FFT scaled very well. So there are very, very hardware efficient FFT implementations. So even later, let us say that after a couple of years, somebody wants a Wi-Fi 9 with 640 megahertz. Yes, the FFT will scale and the bandwidth will be able to accommodate it. But I'll again hark back to one topic. Okay, you can do a lot of things on the physical layer pipe, but if you don't get enough latency, people will not accept you. The market will not accept you. Okay. Now coming to the higher order modulation, which is the third question Dr. Srikanth has put up. Currently, I'm aware that Wi-Fi 8 and I think Wi-Fi 7 also, they support 4096 QAM in the standard. You can always have it in your chip and all that, right? Now, what happens is that those of you who know this theory behind this, that there is a constellation diagram. You can have a very dense constellation in that particular area. Now, because of the non-linearities, especially in your RF chip, and you do some filtering and all that, right? Not only Gaussian noise, not only the thermal noise, you also get some kind of a noise around every constellation point, and that becomes your EVM ball. Now, this EVM ball is agnostic of your constellation. It will be there for BPSK, it will be there for 4K QAM. Okay. Say you want to go to the next order, you want to go to like 16K QAM, right? The EVM ball will not change just because you happen to make it more dense. It will remain the same only. Okay. Now, if you want your EVM ball to shrink, like I said, the problem is not in the baseband chip, the digital chip. The problem is in the RF chip. Okay. So those who are experts in RF design, especially analog design, right? You need to make sure that the distortion that's happening along your RF transmit and even the receive path is kept minimal. Now, if that can be brought down by 3 dB, like I mentioned, like if it's minus 38 dB for 4K QAM, if you can bring it to minus 41 dB for 16K QAM, okay, point number 1. Point number two, you have to make this consistent across PVT. So in the silicon world, there are variations in parts. You have fab, you have different chips, voltage, temperature. Okay. So having consistent EVM across PVT is what you have to achieve in RF design and even the fabrication yield and all that. If you can get that, yes, sometime later we'll be able to 16K QAM. Okay, and there itself you will get a better increase in your throughput. So like I said, it's always a joint optimization and it's a mixed bag thing, which you have to look at when you approach physical layer.
Thanks. Again, any questions? So again, please keep putting up your hand so that Mike can come to you fast. So there are hands, mic runners, whomever you can get to fast. In the meantime, maybe I'll just ask you to comment on that. So I had asked, is this complexity worth it? In the sense that people say that now you mentioned about the baseband complexity maybe not that big,
correct,
but now we are transferring it to the RF side to make it complex to achieve all that things. So is this worth it for the ultimate benefits? What are your comments?
Okay, I think the people who use Wi-Fi should say, okay, like, see, the thing is that when are you hungry for bandwidth, right? I mean, definitely not for some kind of a voice call, right? You do want to have applications like, interactive video calls with higher resolution, right? People want to go to 1K, 4K TV and all that, right? Gamers who definitely want high resolution. So what will happen is that as long as the Wi-Fi industry, architects and designers see the need that yes, the market is asking for better and better rates, lower and lower latencies, okay, I think this is going to happen. Like there's a push for it, yes.
Vijaya?
Yeah. So we have coordinated beamforming coming up in the next Wi-Fi 8, right?
Correct.
What are the challenges?
See, the challenges there are multifold. What will happen, just for the audience's knowledge, right? Here we will have multiple access points, the base stations, who will coordinate, and all these stations in their BSS or cell, okay, will have to get higher and higher data rates. So you want to kind of do joint beamforming. Okay, basically you can think of one student and you can have multiple masters. They're teaching him knowledge and all that. Now the thing is that the access points have to exchange, okay, the information of the channels from each of them to that particular client in a very, very efficient manner. Okay, that's point number one. Let's say you somehow achieve it. Okay, what's more trickier is the timing part.
Exactly.
All the access points have to be synchronized. Though there are lots of protocols of timing, you can do over fiber, you can do, I think, IEEE 1588. There are many protocols and all that, right? I think what has to happen is that the Wi-Fi architects and those who actually deploy the timing standards, the network sync and all that, right? They have to come together, decide how to solve the timing problem first, okay? The third thing is the frequency offset. We'll have different carrier frequency offsets and sampling frequency offsets between every pair, right? So, like I said, nothing is challenging mathematically. The challenge is to make it work in hardware and software. Okay.
Thank you.
Thank you. Yeah, Shashank.
Hi, sir. So, Shashank this side.
Yeah.
When doing an RF design for an AP, which one do you think is more better in like certain scenarios, whether it's a discrete-based design or an FEM-based design? Are there scenarios?
I'm not much aware of, good question. I'm not much aware of the intricacies of RF design. But what I would say is, see, there are two parts of the spectrum, right? Like I said, we can go the heavy beast, we can go the elephant way. So the elephant way is where, you have an enterprise access point, and let us say somebody tells you, you know what, go and design the power amplifier. There was a question asked, right, for 8 streams, Ensure that you have got good linearity, no matter what the center frequency and what the bandwidth is and what the modulation is, right? That's one part of it, okay. What I would say would be a little more challenging would be you go to the IoT space. You go to the IoT space and you try to integrate a lot of the front-end components on the transmit and the receive both. Okay. So for example, can you have an integrated design for the mixer and the power amplifier in one single shot, right? It kind of should be possible. Some people, they want to also integrate the DAC and the power amplifier. The upsampler and the power amplifier. There are lots of things happening, and like if you like search hard enough, on Google patents and Google this thing, you'll definitely get some. So I don't want to give you a particular choice about the choice, like discrete versus FTM. Okay, what I would rather say is that you look at some top 10 universities who do research in RF design, practical research, by the way. Okay, and see which kind of suits your taste.
Okay, I think we'll take a pause here and finish the last discussion item, and then maybe we'll bring as many questions as we can.
So I was actually waiting for this question, Dr. Srikanth. Okay, so I'll tell you what, just for the audience, because I've been working in this for a while, right? See, when you start learning about the physical layer of Wi-Fi, L1, you really get enamored by the mathematics, because that's probably the most beautifully rich. Even the IEEE standards have mathematics in it. They'll have matrices and lots of equations when you go from before the I-50 to after the I-50 and all that, right? So on the one part is okay, fine, there's OFDM, there's MIMO. You know, you can spend probably 1 year understanding the mathematics behind it and doing it, right? Second problem is putting it in hardware, okay? Now what happens is, even in hardware, a lot of people, they get enamored by the digital baseband design because we can do lots of things in modulation, demodulation, decoding, you know. We have LDPC, we have BCC, so on and so forth, etc. My recommendation for those who are both in, you know, students and even industry is that, you know, go to analog, go to mixed signal design, because that's where the next frontier is, okay? So if you can try to really come up with efficient, power efficient, as well as performance efficient designs on the RF part, doesn't matter what component, doesn't matter what, transmit, receive, power amplifier, or mixer and all that, right? If you can come up with some really good designs for that, which can be made, hardware realizable, that will be great, okay? Let me go one step ahead. What happens here is that, see, there are lots of work even in joint digital baseband design and analog RF design. People do that. You can see papers from IEEE journals, conferences, and even in industry, those are working, right? The next frontier of Wi-Fi is millimeter wave, okay? I'll tell you why. So what happens is that after some point, after a couple of years, whether you have 2.4, 5, or 6 gigahertz band, you're going to choke out. You'll keep going, devices are going to get in billions and all that, right? Now, if you want to go to a bigger pipe, you have to go to that 45, 60 gigahertz band. Then you'll get like 1 gigahertz, 2 gigahertz channels, right? Now, how about something where you can architect a device which can work in all the 3 bands? It can work in 2.4, it can work in sub-6, it can work in the 45 gigahertz bands, okay? Now, why can't we have MLO in all 3? It's a fairly technical challenge, okay? Now, both from the point of view of having physical layer, MAC layer joint design, as well as the fact that you want to make some architecture in a form factor for a mobile or for the matter access point, which works in digital baseband, RF, and the millimeter wave regime is not an easy job, okay? I believe that if the industry and the academia move in that direction, that will be the way to go, okay? A lot of work for the next 10 years, I can guarantee you, okay, in this.
Yeah, I think we can have, Vinod, you want to ask the question now?
So the Wi-Fi physical layer itself has a lot of parameters that give different performance for different kind of values. Let's say guard interval, MCS, and NSS, and so on. In a very stationary environment, like let's say there is a home and just one client is there, it's possible to settle down on the good physical layer parameter combination, what's good for that single client.
Correct.
But let's say as the number of clients increase even within the home, let's say 20, 30, or in a bigger deployment like an academia and so on, where the number of clients are very high, is it practical for the AP or the station to choose the real right physical layer parameter combination for itself?
See, what I would say is, no, it's difficult for one AP to do it. So typically what will happen is that even if you have a single Netgear or a Cisco box, right, perhaps they have different chips for 2.4, 5, and 6 gigahertz bands, right? They'll have a tri-combo and all that, right? I think what's better, let me give an example in a different way. I won't directly answer the question, right? All of you know that when there are IPL matches, right, we have people watching even on their mobiles because the cricketer is far away, okay? What happens there is in most of these deployments in the stadiums, they simply use access points in a mesh with only 2 streams. Forget 4 streams, okay? The beauty there is how you get this mesh network, how you get the latency is very low and all that. So even at the level of a stadium where there are sometimes 10,000 to 1 lakh people and most of them have their mobiles, okay, you are able to give at least at some resolution the downlink feed to that particular user, okay. So what I think is that depending on the particular, I would say, deployment and the use case and all that, the problem may not be in hardware, the problem may be more in software and architecture of the network and all that. So stadium Wi-Fi is very different from home Wi-Fi, different from millimeter wave Wi-Fi. That's what I would say. Single AP in home can't support 20 devices. I think it's very challenging, even if you use OFDMA and all that. So you have to form a self-organizing network, like a pack of three different APs and all that. And that's what I think the lady asked here. You can use COBF. Perhaps it will help. Okay.
1 or 2 more questions. Put up your hand. Let the mic come to you. Is 60 gigahertz going to be realistic in our timelines? While the mic
yes, it's going to be realistic.
Okay, so good.
That's what I would say.
Yeah. So there's mic required there, but you can ask and
see, for those of you who read textbook kind of thing, right, you may be hearing that link budget is a problem because, you have millimeter wave rainfalls or there is the dense vegetation. Thing is that all these are, overcomable, okay. We can always get like better power amplifiers, better receivers and all that. So it's not link budget. It's about how fast you can switch the beams, align the beams in millimeter wave that matters. Okay. Yeah,
Girish here. Do you see role of AI in any of this, like
Like,
Yes. That's a good question. See, okay, let me put it like this. Okay, I mean, I don't work in AI, but I'll just try to put it very simply, right? When does AI help a lot? AI helps a lot when you have got a very, very large state space, and whatever is a conventional technique in hardware, software will not be able to do that. So you have to have, some kind of algorithms where you can classify, you can cluster, and then you can use AI on that. Now, in the physical layer, I think there is little scope for AI, but who knows, things may improve in the future, right? But definitely when you want to do something like scheduling in the MAC layer, user grouping in downlink MU-MIMO and all that, right? That's where I believe AI definitely has a lot of potential. So the higher you go up the stack, MAC, L3, L4, etc., when the problems become joint optimization and all that, now I believe AI, machine learning techniques will definitely help a lot. The thing about physical layer, let's just make one quick point here. With physical layer, now some of the things like, those of you who know about Viterbi decoder or LTPC decoder, right? They're mathematically very, very robust and strong. Okay, they come within 0.1 dB of the Shannon limit. So then you cannot do much with AI, ML, etc. The point is that either you are far from optimal, so you want to use AI, or you have a large state space, or you have noisy data. Right? That's where you want to use AI, ML, and it can be in any layer, MAC, higher layers, and all that.
Yeah, in the interest of time, I think I'll have to stop. Maybe you can contact us.
Yeah, we can sync up offline.
Yeah, thanks, Ashutosh. Thanks a lot.